Good morning, everyone. I see some people are still joining, but let's start as we have quite a loaded program today. So welcome to this mioty webinar. It's about mioty and OMS. Quite an interesting topic as it seems with all the participants we have. Welcome to everyone who is here live. You will have the opportunity to ask questions at the end. That's your benefit of watching this live. The webinar will also be recorded, so you should be able to look it up later as well. So you don't need to write everything down. And yes, if you have questions, please use the F&A section in this webinar. So you can just type your question there. And at the end, we will go over the question with the experts. My name is Micha Burger from the mioty Alliance. We are organizing this webinar together with our members, DIEHL Metering. So there, Thomas Blank is our expert. He is working for DIEHL Metering already more than 20 years as a system architect. He has a lot of expertise in protocol design in the upper layers, working with the standardization of MBUS since the beginning of the OMS group, and was even involved in the ETSI standardization, so a perfect expert to tell us something more about the history of OMS and mioty, the different variants and the architecture. And then we also have Jakob here, a co-founder at DeviceLab, also software architect and working with the wireless protocols in the metering space with the different ones and developing several parsers. So he will go more into the details of payload afterwards and show us some examples from the practice. So stay tuned for that as well. Good, welcome. I will hand over to Thomas then.
Okay, yeah. Thank you, Micha. Good morning, everybody. As I said, I'm Thomas Blank from DIEHL Metering, and I will now show you some insights and backgrounds of mioty for OMS. I hope you can all see my screen now.
Yes, it is working.
Okay, perfect. Then let's start. So I prepared for you an overview of mioty for OMS, and we'll show you some protocol stack details. We'll show you some system architecture consequences, and last but not least, I will give you some background and insights. So starting with the overview, mioty and OMS started their work together in 2021, where they signed a liaison. So it's a history of 5 to 6 years. Both groups work together. For those of you who do not know the OMS group, it's a group of manufacturers and utilities that come together to define an interoperable metering system. And that is the goal of the OMS group. And it is based on MBUS, wireless MBUS, on the EN 13757 standards family of wired and wireless MBUS. And this is the basic for the OMS group. And out of the lot of possibilities in those standards, the OMS defined specific requirements for end devices with the goal at the end to be interoperable. Yeah? And as said, both groups did this liaison in 2021, and they created so-called end-to-end solution for interoperability, and this is called mioty for OMS. And as you see here, all this definition for this end-to-end solution has been written down in this mioty paper, the generic sensor end-to-end profiles. This paper is, I would say, the basic for all the topics I explain you today. So don't forget to have a look into this paper afterwards. Okay, this interoperable solution, mioty for OMS, has 2 subprofiles. There are 2 styles how you can integrate OMS and mioty. And one is called OMS LPWAN splitting mode. On the left side here, this is based on the so-called variable MAC. And this variable MAC possibility is defined in this ETSI specification. That is the basic for the mioty TSUNB technology. And on the other side, you have the OMS over mioty sub-profile. And this one is based on the so-called fixed MAC in the ETSI specification. So those profiles, they are using the same physical layer. They are using the nice mioty radio technology. And the OMS has described how to apply it. On the one hand, the OMS LPWAN technology, this is described in the Annex Q of the OMS LPWAN specification. It was released in end of 2023. What I see here is the latest version from December last year. And on the right side, you see the specification of OMS over mioty. This was specified in a technical report OA of the OMS over mioty, also in 2023. So those approaches are defined in the OMS group as well. So now let's dive into some more details of the protocols. And I'm starting here with the OMS LPWAN splitting mode. And what we can see here are the lower layers of this protocol stack. And the orange layers here, physical and MAC, are defined in the ETSI specification. That is the basic for the mioty technology, the TSUNB protocol specification in the ETSI. And out of this, we are using in this OMS or LPWAN splitting mode, we are using the physical layer, as I already said. And this is well known. And important to understand is that the splitting mode is based on the variable MAC, as I mentioned, and this is introduced with the field called M mode, MAC mode field. It's a 2-bit field, and if this is set to 01, then it introduces the variable MAC on the MAC layer level. That means this MAC layer here has just one byte, the so-called MAC type byte. This is identifying which kind of variable MAC is applied. And in this case, it's the wireless MBUS MAC layer that is introduced with this MAC type 02. And now above this line, you have the other definitions of the of the next layers. And you can find those definitions, as I already said, in the Annex Q of the OMS LPWAN. And here now you can find this wireless MBUS MAC that was defined in the last years by the OMS group. And it consists of MAC control fields and a MAC CRC, for example, a 4-byte MAC CRC, some other MAC layer fields as well. I did not show all the possibilities here. And this is introducing a link layer, a logical link control layer that is very identical to the typical MBUS link layers, containing a C field, a control field, containing manufacturer and address fields, and an access counter field, and then last but not least, the data payload, which is in the upper layer. These are the typical MBUS coded data points for metering values. Yeah. So this is OMS LPWAN splitting mode. Let's now have a look to the OMS over mioty subprofile. And as you see, it's different here. This profile is using more definitions out of the ETSI specification. It's using all those lower layers from the ETSI spec. And as said, it's introduced here with a MAC mode field 00 that indicates the so-called fixed MAC. And this fixed MAC means all those fields here are defined in a fixed way, to apply it in a fixed way as defined in the ETSI specification. And yeah, those fields are MAC header fields, address fields, counter and signature security relevant fields. And for this OMS over mioty approach, you have this MPF field, MAC payload field, and this is indicating how it's going further in the upper layers. And here it means the value 83 is pointing to a so-called MBUL. the link layer here, which is an optional thing in mioty in principle, can of course be as well there. And now in the upper layers, you exactly see this MBAL that is introduced here. This is a MBUS adaptation layer. This MBUS adaptation layer is defined in the EN standard, one of the MBUS standard families, the -8 document. It's defining those adaptation layer that is necessary to glue those upper MBUS layers to those IoT technology specific lower layers. It's just 1 byte. It's a small thing. How it looks exactly, Jakob will show you later, give you some examples how this really looks like in a byte structure. And this MBAL layer here is just gluing this, as I said, these upper layers that are equal to the OMS LPWAN splitting mode. It's using the same upper layers here. So if we compare it one by one, you see that mainly the physical layer here is identical. Of course, not the M mode field, but the rest means the radio technology is exactly the same. And what is also identical is the way those metering data points are coded in these upper layers. So the main differences between those two approaches are, for example, the addressing. Whereas in the OMS LPWAN, you will find the address field here in this logical link control layer of the OMS LPWAN. You will find addressing on the right side for OMS over mioty here down below in this fixed MAC definition of the ETSI. And on top of this, you also find an address field in the upper layer. I will show you some more details soon. Another difference, another main difference of these two approaches is the way how security is applied. In the OMS LPWAN splitting mode, you have OMS defined security profiles. They are placed on the transport layer, one of the upper layers here, so-called security profiles, symmetrical security profiles, and they are placed in the upper layer. On the OMS over mioty, you will have the same security here on the upper layer for the OMS security profiles. But additionally, you also have security topics down below in the fixed MAC here. Some more details will now follow in the system architectures. And this is a system architecture exactly pointing to this security topic. So in the upper line here, you see the OMS LPWAN approach. And in the end device, you have a symmetrical master key, and the same master key is available in the backend system, in the automated meter management head-end system, AMMS. And this security is an end-to-end security. There's no need for an OMS gateway to have this key. So the secure data are running from the OMS end device to the backend system. So what is the difference now in the OMS over mioty approach? You may know that we have the mioty network security here, and the network key is provided via the service center, application center down to the mioty base station. And that means the radio technology here, the radio frame on air, is additionally secured with the mioty network security. But as this network security is ending at latest in the mioty service center, you need additional security on top of that to have this end-to-end security guaranteed. So that's why the OMS communication security, those security profiles, they applied on top of the mioty network security in this approach. The other difference that I pointed out was the addressing. And in OMS LPWAN, we are using the well-known MBUS address according to the MBUS standards. And this is an 8-byte address built up with some information about manufacturer, an 8-digit number, a version field, and a device type. For example, here it's a DME, is a DIEHL metering meter, a water meter with this 8-digit serial number. For OMS over mioty, it's different. As you see, it's applying the EUI 64 address according to the IEEE. That has a different approach here, and you also have the organizational unique ID, the DME here, but you see it's different coding with 3 bytes and other bytes like in the MBUS address. So these are 2 different addressing styles in general. And what does it mean for the system architecture? For OMS LPWAN splitting mode, you have this metering MBUS address here in the OMS end device, and it's going through to the backend system that also has this MBUS address, and this is the main identification of this metering point in the database of this backend. In OMS over mioty, you have to handle both addresses. That means a meter still have his metering address, the MBUS address, but additionally integrating mioty, he needs the EUE 64 address here in this approach. And that means it will be forwarded via radio and the mioty base station to the mioty service center and application center. And what needs to be done here is the address mapping. That means this EUI 64 address needs to be assigned to this MBUS address. Both are contained, at least in the startup frames and installation frames, at least you must have both addresses, and then this assignment can be done in the mioty service center. And if you then forward the upper layer data to the AMM system, to the backend system, you will just forward the MBUS address, as this system is only aware of the MBUS addressing. And if you want to send, for example, a 2-way configuration command down to the meter from the backend system, you will just add the MBUS address, and you need this mapping table here in the mioty service center application center to be able to send this to the correct meter, as the identification in the radio network is the EUE 64 address. So this is a bit more, let's say, things to be done in the OMS over mioty approach. What is possible is that you combine those sub-profiles in one system. It's possible to do that. What is necessary to be done are all these requirements shown here and described again in this generic sensor end-to-end profiles document. Here you can find all the requirements for all those system components. For example, the mioty base station has the requirement to be able to understand variable MAC, or better said, to pass it through. So this is a requirement for every mioty base station in the meantime, that it's able to support also variable MAC. And in the mioty service center, you need, as I said, to do this address mapping. You need to be able in this approach to handle this wireless MBUS MAC layer as well. Of course, also the fixed MAC of the ETSI definition, but also the wireless MBUS MAC definition. All these things need to be done in this service center. And the OMS security, you can do it here in the service application center of mioty, or you can pass it through and let it be done by the AMM. So both is possible. So a combined system is in principle possible. So now coming to some backgrounds, and I guess maybe one of the most discussed questions: why do we need those 2 variants? Why do we have 2 sub-profiles for OMS and mioty? And the answer is that each of those sub-profiles is optimized for a dedicated purpose. And the OMS LPWAN splitting mode approach is intended for metering systems, whereas OMS over mioty has the idea to be perfect for smart city systems. I give you some more details here. So OMS LPWAN splitting mode. Why do we have it? I mean, OMS is historically grown, and it started 20 years ago with metering architecture backgrounds, as said, based on MBOS on this 13757 family. And since those 25 years, there are more than 100 million end devices in the fields that are based on remote reading on wireless and wired MBOS as well. So a lot of devices out in the field. And due to that, we have thousands of systems that are operating those meters since decades, yeah. Also, since 20 years they started up. And all of them knows how to work with this MBOS address format. And all of them are using this MBOS address as their identification, yeah. They don't know how to apply a UE64 address in their system. So that's why it's intended for those systems and optimized for them to use OMS LPWAN splitting mode. Since 10, 15 years, these metering systems, they also know how to apply those OMS security profiles. They are also introduced 15 years ago. And in the meantime, all of the system, I would say they know how to do that. So OMS LPWAN fits perfect into those systems, and it's just using the nice mioty radio technology as a physical representation of maybe the former wireless MBOS mode C or T. It's just changing from a wireless MBOS mode C to a LPWAN radio technology, and the rest of the system stays the same, more or less. Of course, as OMS has done those definition of in the Annex Q of OMS LPWAN, there are also some more new MAC functionalities now introduced in this wireless MBOS MAC layer. For example, you can do clock synchronization and, of course, link management of the different technologies of OMS LPWAN. And yeah, last but not least, the variable MAC as it is defined in the ETSI, that's exactly in the specification of ETSI, exactly to this approach, that you be able to do other systems on top of the mioty radio technology. And last but not least, come to this OMS over mioty slide. Why do we have OMS over mioty? So OMS over mioty, it was, I would say, the obvious way to adapt OMS upper layers to a mioty lower layer stack as defined in the ETSI spec. Yeah, all those definitions of the lower layers was specified in ETSI, and it's just that you need, as I said, this small adaptation layer, this 1 byte, to put those stacks together, the lower stack of the ETSI and the upper layer stack of OMS. And this is perfect for smart city IoT systems that are already in the market. That means systems that are integrating also other kind of sensors, parking sensors, pressure sensors, or whatever. Yeah, systems that are aware on how to use a UE64 address. They can easily adapt metering devices with OMS over mioty into their smart city system. And even this address mapping is probably already applied in those systems and not a big issue for them. So as said, OMS over mioty fits perfect into those systems. And it was in 2021 also a matter of time to get into the market with mioty on metering business, as just using the ETSI definition and the OMS upper layers, put it together, and that was a fast way forward to get into the market, quite fast. So that's it from my side. I guess, Micha, I will hand over now to Jakob, and we will have questions at the end of the session, I assume.
Exactly, yes.
Okay.
So, Jakob.
Yes, let me just share here. Take over. Is it showing now? Yes. Good. So now let's dig into some details of what this looks like. we're going to look at the two different modes that Thomas brought up and compare them to traditional C mode wireless MBUS. First of all, we need to have something to do this on. To make it more concrete, I use the real captured telegram as a basis for this comparison. This is what it looks like when I captured the OMS LPWAN frame. The bottom left here shows what some reception information. The bottom right shows the actual data that was included in this telegram. In the top list here, you can see I added the two simulated telegrams that we'll be looking at through this, and it has all the same information as the two, as the original captured frame. Just for clarification, we won't go into the physical layers. We're just going to look at the MAC layers and up today. So this is a roadmap of what I want to show you. I'll be referring back to this as we go along, so you can see where each of the parts that we're looking at will belong in this roadmap. Start with an overview, then build up each of the pieces here and put it all together at the end. Now, I'll keep the roadmap here at the top, as you can see, and you can then always follow along. This is the complete frame that we're going to work towards. If you look closely at this, you can actually see that a lot of the pieces are the same for all three modes, so we don't need to change everything. In the views that are showing all the frames like this, and in comparison, I've included both the encrypted and unencrypted mioty telegrams, just so you can see better what is actually the same in all three. Now let's look closer at the details of this. First, we're going to start at the beginning. In the start of the telegrams, we have some information about the type of telegram and the address of the devices. Now, as we heard before, for OMS over mioty, we don't really have the device address here. We have the local address used for the communication with the base station. We'll get back to how we handle this. Looking at the start of the wireless MBUS frame, as we see here on the right, it has an address which tells you details about which meter this telegram is from. It's also a control byte saying this is data frame that does not expect a response and was broadcast autonomously by the meter. We're using frame format A here for the representation in this example. Now let's move on to the OMS LPWAN version. For OMS LPWAN, it gets a bit more complicated than what we're used to. First, there's a MAC layer, which can be used for network management tasks or for synchronization, as Thomas was explaining. The MAC is also responsible for frame integrity by adding a CRC at the end. We'll get back to this. Since this is a data frame from a unidirectional meter, we're using the most basic of MAC headers here. It's followed by a link layer in frame format C. The link layer is more configurable than the frame format A we just saw, and that is handled by what's called an LC field. It declares what's actually in this frame format C header. We have the control and address included directly from the wireless MBUS frame, and additionally, this meter is using extra ATC frame counter at the link level. Moving on to the OMS over mioty frame. Here we're using the standard mioty MAC. We need the device to fit into a standard mioty pipeline, like Thomas was explaining. So this can be used there with a fixed MAC. First byte is a control that just describes this MAC frame. In this case, we don't have any sort of additional segments, so it's just a simple one that has to enable the MPF or MAC payload format that was mentioned earlier. We need to add some network level address here for the local communication. And I should also say there is a message counter here called MPDU count, which is used to maintain the security guarantees at the network level. For this example, I used the same one as we'll see later in the some of the OMS type layers. But normally you would make sure that this fits your application. The important part is to make sure you don't use the same MPDU count more than once. Next, for the OMS or mioty, we need the adaptation layer that was mentioned earlier. The MPF for that is, as we saw, 83 hex, which we can see here. There is over here. There is the actual MBUS application adaptation layer is just a single byte. It has a function which represents the same as the control we were seeing for the two other frames. Here it's just compressed so that we can actually use it for other information as well. Now, this was all for the initial information in the telegrams, which is where the biggest difference between the three lies. So now we carry on to some information that is shared between all of them. The first part of this is what we call authentication and fragmentation layer. Here you can see what that looks like in the different telegrams. Here we have what information this actually is. It contains some security information to make sure that data in the telegrams are not tampered with on the way to the backend, so ensuring this end-to-end encryption and security. It is mandated by the encryption mode that we'll be using, which we'll come to next. It can also be used to split the data over multiple smaller telegrams if you need this, because the underlying radio layer doesn't support as large frames. Now, for the mioty radio layer, we do support the large enough frames for this, so we're not going to use this fragmentation here. The individual sections inside this OMS payloads has what's described as a control information or CI field. For the AFL, which we just mentioned, this is 90 hex. The AFL has two control fields that describes what is actually in this part of the layer. One FCL is for the fragment, the other MCL is for the entire message. They are, in this case, equal because, as I said, we're not using fragmentation at all, so everything will be in this one fragment. On the right here, you can see what this looks like packed into the telegrams with the message control, which is the same as the one we had earlier in this example, and some message authentication as mandated by the two control fields. Now, moving on to the next section here, we have more shared information. In this case, you can see by the OMS over mioty that there's a small difference. We'll get back to what that actually is. If we look at first the standard transport layer, which we just saw here, it tells the receiving decoder how the data is encoded and encrypted for confidentiality. Again, this section is designated by CI, here it's 7A. One important detail here is the ACC telegram counter. For encryption, we use this one instead of the one we saw earlier in the OMS LPWAN link layer. There's a bit more detail in how the actual encryption is handled than we could have time to go through here. So you should always consult the standard when you design your individual telegrams. Now, we mentioned that we will get back to the address handling problem for mioty end devices where you need to have this mapping between the mioty and the OMS address. OMS really, in the technical report number 8 that they released, details how to use this OMS over mioty, and they also bring some suggestions for how to actually do this address handling. In this case, we're going to be updating our transport layer to actually include this address, and this will make sure that all telegrams convey the same information. And as you can see here on the right, what we do is we change the CI to one that actually supports this address, and then we add the addressing information before the header information that we already saw with the existing transport layer. Next, here is, well, a lot of hex data. This is the encrypted application data. The interesting thing to note here is this does not change for these three telegrams because we want to still maintain the same level of security. This also means that if one were to actually build, one would like to build a converter from one of these forms to another, this could actually be possible with the small exception that, of course, the OMS over mioty adds some extra encryption at the network layer on top of this, which you need to be aware of. Now, just for reference, this is the application data before and after padding and encryption. It's just so you've seen it. We won't dig too much into this. Now, and as well for reference, this is what information I used for the encryption of the mioty telegram. So you can actually repeat these experiments if you wish. And with that, we come to the end of the telegram, where we have some additional CRCs and CMAC used for data integrity, as I was saying earlier. And all of these are, of course, done on the encrypted telegram, so you can verify them before decryption. And here we arrive back at the actual full frames again, where you can see all this information. And this, we've gone through all the sections now and can see how they fit together. Thank you. That was pretty much what I had. The screenshot we had at the beginning, I should probably say, were from our payload collector app, and we used our advanced collector sniffer just to capture those. Thank you.